The density of seawater is another important scalar property, usually denoted by the Greek letter rho. And it's a function of space, x, y, z, and time in general. Now what is the density? What is density of anything? Density is the mass in a given volume, or the mass per volume. So if I have a volume of size 1 meter on each side, so that's 1 meter cubed, and if the mass of that is 1,000 kilograms, then the density of that is 1,000 kilograms per 1 meter cubed, or 1,000 kilogram per meter cubed. Now, so the volume is important. How much mass is in a given volume is important. And for ocean water, we want to know the density because the density influences the stability of the water column, and differences in density can drive currents in the ocean. The problem with density is it's very hard to measure. If you wanted to collect a sample at 4,000 meters and say what is the density of this fluid, you'd have to get it back up to deck without influencing the volume, even undergoing a large pressure change, and weigh it accurately, on the rolling ship of a deck, just to get one sample. And so it's just too tedious to do. So what is generally done is to use an equation of state to compute the density. Now, in most cases, you will see the density described as having units of kilogram per meter cubed. That's typical today. This equation of state takes into account temperature, salinity, and pressure, and its influence on density. And this, over the years, there's been an enormous investment of energy into coming up with better and better functional fits. So this isn't physically based. It's essentially an empirical fit to a large amount of data that describes density as a function of those three variables. Now those three variables can be measured very rapidly in situ using even a single instrument like a seabird, which carries a temperature measurement, conductivity salinity measurement, and a pressure transducer in order to get at pressure. So those three variables can be measured in one location on the fly. Now, the equation of state that's typically used in most computing software is quite complex. It has polynomials of temperature and salinity on the order, I believe, of exponents to the 5th power, including combinations of salinity times temperature, etc. So it would take several screens to write it all out. But what we can do locally is linearize the equation just to see the influence of temperature and salinity and pressure on density. So this is just a local linearization so that the dependency of density is only linear on each variable. It's linearly dependent on temperature, salinity, and pressure. And you see the coefficients of the linearity A, B, and K. Now A is negative. That implies as I increase the temperature, the density will go down. A warmer fluid, seawater, has a lesser density than a colder bit of seawater with everything else held constant. Coefficient B here is roughly is positive. It's approximately equal to 0.78 when we linearize around this particular point in state space. Is positive, so as the salinity increases, the density increases. You get more salts in the sample, you have a higher density. And as pressure goes up, density goes up. So it's also positively correlated with pressure, which shouldn't be surprising. So we have a negative correlation with temperature and positive with salinity and pressure. And we can look at these various constants, in particular looking at temperature and salinity, and this gives us an idea of how much the temperature has to change in order to change, say, 1 kilogram per meter cubed of density. What does delta T need to be? How much salinity, how much does the salinity have to change in order to get that same change in density? That comes from the slopes of the linearity, and those slopes are here, 0.25 and 0.78. Now, for many coastal applications, we can ignore the influence of pressure. The other terms dominate, and pressure doesn't get that large because the depths are not large. There are some cases where you're doing riverbeds or other places where you have large amounts of erosion, and there the sediment itself can become suspended in the water column and influence the density. There are density-driven flows, particularly during storm events, places like Taiwan, where you have massive storm events and river runoff, and you get these high, dense suspensions of materials that actually drive the flow. The standards are maintained by UNESCO, and if you Google around for equation of state calculators, there's a whole bunch of them on the web where you essentially can plug in temperature, salinity, and pressure, and out pops your density. And there's also functions. If you want to have a whole bunch of temperature, salinity, and pressure data, and you want the density, you can grab one of these functions where they've taken the UNESCO polynomials and programmed it into a piece of code. These are available all over the web. For example, MATLAB, it's contained within the Seawater toolbox, which is freely available. Now, most seawater densities typically in this range. Freshwater is in the around 999.5 to 1,000, depending upon temperature. Seawater, because of the higher salinity, is between 1,020 and 1,030. So that range comprises a good bit of the ocean, maybe 99%, maybe more. So it's common to use what's called sigma density, which is that density minus 1,000. So if you see something reported as sigma equals 20, that implies that the actual density is 1,020. So if you're looking at the difference between two places, you can subtract two sigma densities. It's the same as subtracting the two actual densities, the real densities. Where you have to be cautious is any place you divide or multiply by rho, there you would want to use true rho instead of sigma. So it's just a convenient way instead of having to keep writing 1,000 when there's always 1,000 there. With the ocean layers, we can also define the sigma t. So here we've subtracted the influence of pressure, and so we can think of this like the surface density. We have salinity and temperature at 0 pressure. That's known as the sigma t layer. Here's some sample density profiles, and these may or may not be typical of the ocean near you, but just to give an example of how salinity and temperature, this is temperature here, and salinity are combined to give you density. Here we have temperature. In this case, it happens to be warmer near the surface. We have what's called the thermocline. So there's a portion of the water column over which the temperature is rapidly varying away from the surface, and then the gradient slows down, and we have a very small gradient of temperature where it only decreases very slowly as you head towards depth, 4,000 meters being essentially the abyss. We can do the same with the salinity. This is a more complex salinity field where we have high salinity overlaying a salinity gradient, which we call a halocline, down to lower salinity water down here. Now the higher salinity water is denser at higher salinity, but we're offsetting that effect by having higher temperatures, which lowers the density. The result being, in this case, that the surface water is the least dense, and the density increases with depth. And you see the same thing. We have a region over which the density is most rapidly changing with depth. That is, the density change per meter of depth is greatest, or you have the largest gradient, and that's known as the pycnocline. And then it sort of slacks off as it goes into the deeper part of the water column. So even though the salinity at the surface is higher, we can still have a stable profile provided the temperature is warm enough to offset that. Now, in a stable water column, we necessarily need rho to be constant or increasing with depth. So this is a stable profile because we can see that the density increases with depth. And we can think of that as if we take a chunk of a meter cubed of water, here, 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 the weight of that, or the mass of these chunks, is going to increase, as long as they're the same volume, as we go to greater depth. So we have lighter chunks stacked on top of heavier, which is a natural, stable configuration. The phase, so this we can wrap this up discussing the phase of water, or phase chart of water, seawater, at 1 atmosphere of pressure. So we're ignoring the effects of pressure for the moment, and this gives you an idea of the more complex relationship between density, salinity, and temperature than we saw in our simple linearized case. So it's more of a, so you can imagine a surface in 3D. And so we see here that at constant temperature, so here's temperature equal to 20, as we increase the salinity, we see we're going across larger and larger sigma surfaces. So this is sigma. So this is density at the surface, sigma t equal 1005 kilogram per meter cube, 1010 kilogram per meter cube, 1015, etc. So with the increase in temperature, with the constant temperature, the increase in salinity gives us a higher density. And we see the same if we look at fixed salinity and simply decrease the temperature. We see that we're moving towards surfaces of higher sigma t. We've gone from crossing 20, or 1020 kilogram per meter cube, and we're approaching 1025 here. So the same thing occurs. So those, we've already examined those two things before, that higher temperature is lower density and higher salinity is higher density. Also note that it says here that 90% of the world's ocean lives in this tiny little box here. So the world's ocean is confined to a pretty narrow band of temperature, salinity, and thus density. The complications occur around freezing, because at high salinities, provided it's higher than around 24.7, as we decrease the temperature at a given salinity, so let me go back to our line here. So say the salinity is 30 ppt. As I decrease the temperature, I'm going to higher and higher sigmas continuously until I hit freezing, which occurs at a salinity of 30 around -2 Celsius. So having the salts in the water will lower the freezing point of the water. But the key thing is, as I lower the temperature, the density continues to increase until it freezes. If I'm below this point here of 24.7, I have a slightly different phenomenon. Let's take it down to 10 parts per thousand salinity. As I lower the temperature, the density increases, and I can imagine here just for a second that I have other density surfaces in between here that are sort of mirroring. Here that might be 9 and this might be 8. So as I decrease this temperature at a given salinity, the density is increasing until it reaches a maximum point right here. Now these isopycnal lines, these constant density lines, are veering away. They're starting to curve back. You can see how they basically, let me exaggerate, it looks like this. Here's that point of maximum density. So density has now reached a maximum, and if I continue cooling it, it actually decreases until I hit the freezing point. So the solid water is actually a lower density than the water at around here, or around 2 or 3 degrees Celsius. And what that means is that ice floats, provided the salinity is less than 24.7. Now, even in oceanic water where we have salinity higher than 24.7, as the ice begins to form, or we begin to cool the water, we have ice formation and brine rejection, and locally we are going to have very low salinity. So we will have ice that floats. It's an important phenomenon because that floating ice essentially insulates the water below it, and reduces the amount of solar radiance that can actually strike the water. So it changes drastically the dynamics, reduces the wind forcing on the water. So having the special property of water such that the solid phase floats on the liquid phase is pretty important to the dynamics, at least in the colder latitudes. And we see here if we have zero salinity, so this is fresh water like a lake, and you cool it down, the densities keep rising until you hit this point of maximum density right here at about 4 degrees C. And then the density starts to decrease, and then it freezes here, of course, at 0 by definition. And so this means it's hard to cool lake water below 4 degrees because it just keeps sinking and sinking and sinking, and anything such that the water that's on the top is actually warmer than the water below. And so typically if you go in the winter in a place where a lake freezes over and you cut a hole in the ice and you drop a thermometer down, you'll find that the most of the deep water of the lake is around 4 degrees Celsius, and in many areas it will stay that way year round, because that is the temperature of the densest pure fresh water.